We are going to look at the CORDIC algorithm in this video. The CORDIC algorithm is something that has a number of useful applications in the domain of signal processing, primarily from the point of view of computing trigonometric functions as well as certain other kinds of functions by means of a regular iterative algorithm that is very hardware friendly. We will first start by trying to motivate the problem. What exactly is the problem that we are trying to solve? Or at least one of the problems that we are trying to solve, or what was the origin of discovering the CORDIC algorithm, some possible methods for solving it in the first place, why they are inefficient or ineffective for hardware implementations, and how the CORDIC algorithm essentially solves those problems and gives us a nice way of computing certain kinds of trigonometric functions. So the question that we are essentially trying to solve is, how do you compute the value cosine of a given angle theta and related the sine of the angle theta. The first thing we are going to assume is that I am working with number representation which could be some kind of fixed point . Actually, it does not really matter too much. It could also be floating point. The reason why we specifically consider fixed point is because it makes the kinds of divisions that we are going to do later on even simpler to do. They just become right shifts, right? But we need to have some kind of number representation, and we will also assume that the number representation is such that it has enough number of bits for us to compute whatever the value that we are trying to compute to sufficient accuracy. So those parts, in other words, are not going to be considered in this discussion. So the first and probably the obvious way by which we might go about computing something like the cosine, or based on high school maths, would be to say, let's go with the so-called Taylor series expansion. So cosine of x is going to be given by the value 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial, and so on. We already know what this expansion corresponds to. Similarly, we have sine of x is equal to x minus x cubed by 3 factorial plus x power 5 by 5 factorial minus plus and so on. Both of these are infinite series which are valid as long as x expressed in radians has these are actually valid for any value of x, and in particular for small enough values of x we can easily find that we can actually compute this, and the terms x power 3, x power 5 will themselves be dying out, and the factorials in the denominator are growing so fast that they would essentially make the series converge reasonably rapidly. But in general, that's not good enough. It still means that there's a significant amount of computation to be performed, and it may not always be possible to do this kind of computation in a trivial manner. In particular, there are two things we need to do here. One is to compute the factorial values, and the second is also to compute the x cubed, x power 5 and so on. Both of those involve multiplications, and these are not trivial operations to do easily. So another way of doing this could be to use something called a lookup table. Now, how does a lookup table work? Example, let's say that x is equal to 0.25 radians. Right? What I could do is to create a lookup table where I store values x and the corresponding output cosine x over here. So in other words, when x is equal to 0 radians, cosine x will be equal to 1. When x is equal to 0.25 radians, it will have some value. For 0.5 radians, it will have another value. For 0.75 radians, it will have another value, and so on. Which means that when I get the value of x, 0.25, I just go look it up over here and say this is the output. what happens if I need to do the same thing for x is equal to 0.3? I could still go ahead and say that I will compute the value from the same lookup table, in which case I could then say find out what is cosine of 0. I get a value C1, cosine of 0.25, or to be more precise, let's say I'll compute cosine of 0.25 to get the value C1, and then compute the value cosine of 0.5, I'll get a value C2, and now I can interpolate between these two values, right? One possibility might be to say, assume that I have at 0.25 a value C1, at 0.5 a value C2, and I just say that the value at 0.3 is going to be a linearly interpolated value between these two. Alternatively, I could choose some kind of a more complicated interpolation technique. But at the end of the day, what will end up happening is, number one, the accuracy is limited by the number of points that I have in my lookup table. And secondly, the interpolation itself might end up consuming a lot of computational resources, making this entire business of storing a lookup table and then interpolating not really worth the effort. So the CORDIC algorithm stands for Coordinate Rotation Digital Computer, and you can sort of guess from the name itself, the fact that digital computer and so on are used as part of the name, that this is not a very recent thing, because nowadays we don't even think of a computer as a special unit that needs to be used for computing certain things. We would never really use the name computer as part of the new algorithm. This was basically discovered in 1959 when digital computers were still in their infancy. They were not really used on a large scale, by a person by name Jack Wolder. The application over there was for control of certain kinds of missile related computations, and the interesting thing over there was that it essentially replaced a certain kind of analog computation that was until then being performed. The digital computation, or the algorithm that was proposed over here, was in some ways a lot more reliable, would always give you the exact same result no matter how many times you repeated it. But the best part about it was that it was straightforward and easy to compute, and therefore it turned out to be very successful in a large number of subsequent signal processing applications as well. There are two core ideas that are used in the CORDIC algorithm. One of them is the concept of binary search, or at least dividing your search space, even if not in binary, at least into much smaller segments which converge much faster. The other core idea that is used over here is called strength reduction. In particular, can we replace multiplication by means of a simple bit shifting operation, which makes it friendly for hardware implementation. Now, let's explain the first idea using an example. What do I mean by binary search? Okay. Now, what I'm going to do over here is actually digress away from the question of how do I compute cosine of x. Rather, I'm going to say, given a certain value, given coordinates x comma y, how can you find the angle corresponding to the vector represented by the coordinates x comma y? In other words, in a 2D system, if I have my coordinate system out here and I have these set of specific coordinates x comma y, this length of this line is called the magnitude, and this angle is what we are interested in finding. Okay, so let's say that somehow corresponds to an angle of 70 degrees, right? I do not know this ahead of time, but, and this is exactly the value that I am trying to estimate. Okay, what I can do is to take the value x comma y, or take the point xy and rotate it clockwise by 45 degrees. Why 45 degrees? Well, 1/4 of the quadrant, right? Pi by 4 effectively. It's as good as any angle that you can really think of to rotate by. And since it is basically half of the quadrant, not 1/4 of the quadrant, half of the quadrant, it basically is a logical point at which to start. Assuming that my angle is somewhere between 0 to 90 degrees, I would probably start by rotating it clockwise by 45 degrees. What would this mean? If theta was greater than 45, result will still be in the first quadrant. Right? Where by first quadrant I essentially mean region where x and y are both greater than 0. But if theta was less than or equal less than 45 degrees, the result would have moved below the x-axis to the fourth quadrant, and I can easily see that y would have become negative for the result. Okay. Now, of course, the question becomes, how do you do rotation? This is easy. If I have my input is the coordinates x comma y, then what I can say is rotated coordinates x prime, y prime can be obtained by the following matrix multiplication. Cos 45 degrees minus sine 45 degrees, sine 45 degrees and cosine 45 degrees of x, y. In other words, x prime is equal to x into cos 45 minus y into sine 45 degrees, and y prime will be equal to x sine 45 degrees plus y sine 45 degrees. Note that this is actually a rotation by plus 45 degrees, or in other words, counterclockwise. Right? So what we would actually want is to rotate by minus 45 degrees, which means that we basically need to replace the values that we have over here with whatever other appropriate values, which in other words would basically become cos of minus 45 minus sine of minus 45, sine of minus 45 and cos of minus 45. In other words, if I want to replace by any angle, if I want to rotate by any angle, it's as simple as x prime y prime would be equal to cos theta minus sine theta sine theta cos theta times the original coordinates x, y. So now how does this help us? Step 1 would be rotate by minus 45 degrees and check result y greater than or less than 0. If y is greater than 0 of the result, it means that the angle is greater than 45 degrees. So now search in 45 to 90 or search the rotated value in 0 to 45 degrees. Okay. So in our case, for theta equal to 70 degrees, after rotation, theta is equal to 70 minus 45 equal to 25 degrees. So let's go to step 2. Instead of rotating by minus 45, this time rotate by half of that, minus 22.5 degrees. For theta equal to 25 degrees, this will become plus 2.5 degrees, still positive. Step 3, rotate by minus 11.25 degrees. Why 11.25? Half of 22.5. The result in this case, for theta equal to plus 2.5 degrees, once I rotate by 11.25, I would get minus 8.75 degrees. Now we need to change the direction of rotation, because effectively what has happened at this point is that I started off with a vector which was 70 degrees and rotated it to a vector which now has 25 degrees. In the next step, I took (25 degrees) and rotated it down to 2.5 degrees. And in the third step, I have taken this 2.5 degrees and rotated it to minus 8.75 degrees. So what should I do in step 4? Instead of, now I will once again rotate in the opposite direction, which means that I will now rotate by a positive angle, which is half of 11.25, which is basically 5.625 degrees. What does that look like? My starting point over here is minus 8.75, and I will now rotate it to get this point, which is going to be minus 3.125 degrees. Step 5, step 6, etc. Keep on doing this until that angle essentially converges as close to 0 as possible. And the final angle estimate that I have is going to be (45 degrees) plus 22.5 degrees plus 11.25 degrees minus 5.625 degrees minus plus, etc. Right? How did I come up with this? By keeping track of the series of rotations that I did to start with. I first rotated by minus 45, minus 22.5 minus 11.25 plus 5.625. That corresponds to adding up all of these and subtracting the ones where I had to add an angle. In other words, the exact opposite of the sequence in which I actually subtracted angles from the original starting point. As you can see, the entire process by which I am doing this rotation will finally get me to the point where the rotated xy coordinates will exactly match with my x-axis, and I can estimate any angle as accurately as I want. Of course, this will work for any angle in the first quadrant. If you want it to work for other values of x and y in the other quadrants as well, it's a relatively simple extension to this. One way of doing it is to first look at the values of the signs of x and y, switch them over so that the result falls in the first quadrant, estimate the angle, and then correct for that by finding the quadrant in which the values actually were. I'm not going to get into that detail right now. Okay, so in other words, what this looks like is, if I wanted to estimate an angle, I could go about taking a starting point, doing a series of rotations, matrix multiplications and rotations, and thereby estimating what was the original angle that I had started with. What if I wanted to do something different, which was rotation, right? In this case, what I could do is, I start off with coordinates x comma y, and I have a target angle of rotation equal to, let's say, 70 degrees. Now what I would do is, I would say, step 1, rotate by 45 degrees. Step 2, rotate by 22.5 degrees. Total equals 67.5 degrees. Step 3, rotate by 11.25 degrees, and the total in this case would now become equal to 78.75 degrees. Now I need to rotate backwards. In other words, by minus 5.625 degrees, the total equal to 78.75 minus 5.625, approximately around 73 degrees or so, right? I keep doing this till I'm close enough to 70 degrees. How do I define close enough? This is where the numerical representation and the precision of the numbers comes into the picture. I need to choose sufficient number of bits and sufficient number of iterations so that I have come close enough to the answer that I finally wanted. This is of course left as a choice to the designer. The important point is, I can start out with a given value xy, rotate by some fixed angles, and successively reach the final rotation that I want. So there are two things that I can do over here. Either I can start with a given xy and find the angle it corresponds to, or I can take a given xy and an angle as input and rotate xy by that angle and modify it to a new value of x comma y. So in other words, if I know how to rotate by some fixed angles, for which I could store the values in some kind of a lookup table, I should be able to do my entire computation systematically. So what is required for this? It's those rotation matrices, right? So I have cos theta minus sin theta, cos theta, for theta equal to 45 degrees, 22.5 degrees, 11.25 degrees, and so on, right? All these values need to be stored possibly in a lookup table or in some other way that makes it easy to compute. This is still okay. Hopefully the number of such values that I need to store is not very large. Maybe even if I store around 10 such values, I would be able to iterate through 10 different angles and I should be able to get to closer than 1 degree of computation. Right? In fact, by rewriting this matrix as cos theta into 1 minus tan theta and 1, I would then need to store the values of cos theta and tan theta, right? Let's see if we can simplify this even further, and this is precisely where the intuition used in CORDIC to apply the idea of strength reduction comes into the picture. And what I mean by strength reduction in this case is, can we replace multiplication by tan theta with a simpler operation? And the key insight over here is to say that tan 45 degrees is equal to 1. Tan 22.5 degrees, although not exactly equal to 0.5, is close to 0.5. And tan 11.25 degrees is close to 0.25. So how about if we invert the way that we are going about these computations and say that instead of storing matrices for theta equal to 45, 22.5, 11.25 degrees and so on, let us assume tan theta goes in the sequence 1, 1 by 2, 1 by 2 square, 1 by 2 cubed and so on, and find out what are the corresponding values of theta. In this case it would be 45 degrees, $26.565 degrees, 14.036 degrees and so on. So what would this actually mean? That in the rotations that I described over here, I would still say fine, rotate by 45 degrees in the first case, but the second time around I would rotate by 26.565 degrees, rotate by 14.03 degrees and so on, right? Would I still be able to get the same kind of convergence to the final angle that I had in the previous case? It turns out that yes, you can, because after all the angles that we are considering, that we are rotating by, are always greater than or equal to the half of the previous angle that we considered. As long as that is the case, what we will find is that we will be able to do this iteration using these sets of angles and still approximate any angle that we want with a sufficient number of iterations. How does this help us? The main reason it helps us is the tan thetas are all now inverse powers of 2, and multiplication by 2 power minus k is essentially just a right shift for a fixed point representation of numbers. There is no hardware multiplier at all required over here. all that you need is to right shift the value by k bits. In other words, the multiplication, this matrix multiplication has now suddenly become very easy to implement, except of course for this value of cos theta. What do we do about that? We'll get to that in a moment. So if we go back and once again write what is the iteration that we are going to do, effectively what we would have is start with x comma y. Step 1 would be rotate by theta 1, in this case equal to 45 degrees, right? And this would basically be done by cos theta 1 into 1 minus tan theta 1 1 times the vector xy, where we know that this is essentially 2 power minus 0, right? Step 2 would mean rotating by theta 2, which would be 26.565 degrees, which is cos theta 2 into 1, 2 power minus 1, minus 2 power minus 1, 2 power minus 1 and 1 of the x1 y1 that you obtained in the previous case, and we would get x2 y2 as a result, right? If I iterate through many steps, where of course what I would need to do is to change the sign of the theta 1 or theta 2, or change the sign of this for the tan theta component if I want to rotate in opposite direction for convergence, right? As long as I have done this and I rotate through all of these angles, I'll find that the cos values, cos theta 1, cos theta 2, etc., are just accumulating. And what I would finally have is that the xn, yn values are essentially going to be cos theta 1 into cos theta 2 multiplied out so many times up to cos theta n multiplied by 1 minus tan theta 1 tan theta 1 1, or no, it could be a plus or minus of this, and similarly a plus or minus on the next matrix, plus or minus on the next matrix, etc., as required in order to converge the angles. This part would essentially be 2 power minus 1, this would be 2 power minus 2, and so on, which means that this value that I have over here, if n is constant, if n is fixed, this will be a constant that I can pre-compute. It will be a function only of n and not of the sequence of positive or negative rotations that I follow. This basically allows me to go ahead and pre-compute a certain coefficient and say that by rotating by each of these individual angles, I can end up getting the final value xn yn, which is a ultimately rotated version of the original xy that I started with. So what we can see over here is that CORDIC can be used to compute the rotation of an xy coordinate to x prime, y prime through essentially any angle. Or given xy, estimate or compute the angle it corresponds to, and it turns out that with some minor changes to the algorithm can also be used in order to compute a number of other transcendental functions. For example, the hyperbolic sine, cos, tan, etc. and related kinds of functions can also be done using a very similar kind of approach of the CORDIC rotations. So effectively, in other words, CORDIC forms a whole class of different kinds of algorithms that can be used in order to compute many different functions. The key idea, as I said earlier, is that we use two things. One is the fact that you can use binary search to iteratively reduce the space through which reduce the number of computations that you need to do and converge to a final result. And secondly, we use strength reduction to convert multiplication into a simple shift operation that is very easy to implement in hardware. These two things make the CORDIC algorithm very well suited to implementing these kinds of computations in hardware,